For years, physicists have found clues that do not seem to belong to our universe at all. Energy that shifts without a clear source. Alignments that should not occur by chance. And forces that behave as if touched by something outside our cosmic boundary. When every familiar explanation falls away, one idea remains. We may be sharing space with another reality we cannot yet see. Tonight, on Fall Asleep to Astronomy, we drift through this quiet theory and follow the evidence that first led scientists to consider hidden layers of existence. We will explore how these anomalies appear, what they might mean, and why the idea of overlapping realities is no longer dismissed as fiction. If this gentle curiosity feels right to you, a soft like and a quiet subscribe. Help others find their way here too. Settle in now, and we will follow the thought a little further. You have spent your whole life moving through what feels like a simple, familiar stage. Forward and backward, left and right, up and down. 3 directions that cradle every step you take. When we add the steady flow of time, the way moments arrive and then slip away, it is easy to believe we have the full map of reality. Space in 3 dimensions and a river of time carrying us along. But beneath that picture, physics keeps whispering that something is missing. The equations that describe the universe do not quite sit comfortably together. When scientists try to line them up, small cracks appear. The forces that rule the cosmos do not balance as neatly as we would like. Gravity, the quiet pull that keeps your feet on the ground, and the moon in its orbit, starts to look as if it is holding back a secret. One gentle, unsettling idea is this: perhaps gravity feels so weak, not because it is truly feeble, but because most of it is flowing away into a hidden direction of space that you and I can never turn toward. For more than a century, physicists have been following this possibility. They have been wondering whether the universe carries more directions than the few we can walk through. Extra layers folded into reality, too subtle for our senses to touch. The idea comes from stubborn pieces of mathematics that refuse to behave unless more dimensions are allowed to exist. If those extra directions are real, they could explain why gravity seems so faint, reveal a deeper pattern to the cosmos, and even suggest that our universe is only one sheet in a larger stack of realities. That leaves a question that lingers softly. Are we truly seeing the whole of reality, or only a thin slice cut from something larger? When you look back at the history of physics, you see that progress has often begun with small clues that refuse to fit the story everyone believed. The path of Mercury around the sun was off by a tiny amount. A little wobble that should not have been there. That mismatch eventually opened the way to Einstein and the idea that gravity is not just a force, but a bending of space and time themselves. Another time, the way hot objects glowed did not match the predictions of classical physics. The old equations predicted an impossible flood of energy that never appeared in reality. To fix this, scientists had to change how they thought about light and matter at their most basic level. And out of that change grew quantum mechanics. Again and again, when the universe refused to behave as expected, the answer was not to ignore the discomfort, but to follow it. Extra dimensions enter the story through the same kind of gentle but persistent mismatch. One of the most stubborn puzzles is gravity itself. In everyday life, it feels obvious and absolute. You let something go. It falls. Planets circle stars. Moons circle planets. And everything seems to be quietly compelled toward everything else. Yet when physicists compare gravity to the other forces of nature, it is shockingly weak. A small refrigerator magnet can lift a paperclip, and in that single motion, it defeats the pull of the earth beneath you. All the fundamental forces are supposed to live in the same universe: gravity, electromagnetism, the strong nuclear force that binds the hearts of atoms, the weak nuclear force that governs certain delicate transformations. If they are all part of one cosmic family, why should gravity be the frail one? Struggling to keep up, this puzzle even has a name: the hierarchy problem, because it describes a strange imbalance in the strengths of the forces. One answer is that gravity is not truly weak at all. Its strength may be spread out, shared with places we cannot see. Instead of being confined to the three directions we know, gravity might be reaching into additional dimensions, pouring part of its influence into unseen corridors. What we feel here, in our familiar space, would then be only a shadow of its full presence. The small portion that remains after being diluted across a larger, hidden landscape, gravity may not be failing. It may simply be multitasking, stretching itself across layers of reality that our bodies and even our finest instruments cannot yet access. When physicists write down the equations that describe particles, light, and the nuclear forces, everything behaves neatly within the three spatial dimensions we know. Those equations sit together with a certain elegance. Gravity, however, does not slip into place so easily. It stays awkward, the odd one out, resisting every simple attempt to unify it with the others. When scientists allow for extra dimensions, something surprising happens. The possibility appears that all four fundamental forces might be parts of a single, larger framework that lives in a space richer than the one we walk through. It is as though nature has been leaving a quiet hint in the corner of the blackboard. Gravity does not fit because it is not playing on exactly the same board as everything else. What we have been calling weakness might be the shadow of a deeper geometry, an unseen architecture of space that quietly shapes every moment of your life. From the weight of your body in a chair to the path of distant galaxies. Another hint comes from a bold idea called string theory. Instead of treating particles as tiny, structureless points, string theory imagines them as minuscule vibrating strings, like the finest of threads woven into the fabric of reality. But there is a catch. Those little strings cannot dance freely in a world with only three dimensions of space. When physicists feed that assumption into their equations, the numbers refuse to cooperate. The formulas wobble and break. To restore balance, the theory demands more room for the strings to move. It asks for additional spatial dimensions, at least 6 extra directions curled up so tightly that we never notice them in everyday life. It is not that scientists chose extra dimensions because they sounded exciting or strange. The mathematics pushes them in that direction. If you take those hidden dimensions away again, the carefully built framework collapses. That requirement is a quiet clue that there may be more going on beneath the surface of the world than we can experience directly through sight or touch. The idea of using extra dimensions to bring forces together is not new. In the early years of the 20th century, two physicists, Kaluza and Klein, tried to weave gravity and electromagnetism into a single fabric. At that time, only those two forces were well understood. They began with Einstein's description of gravity as the curvature of space and time. And then they added one more spatial dimension into the equations: a fifth direction beyond the three we move through. To their surprise, when they did this, the mathematics naturally produced not only gravity, but also the familiar equations of electromagnetism. Out of one higher dimensional geometry, two different forces appeared, like different shadows cast by the same unseen shape. The idea eventually slipped out of the spotlight as quantum mechanics rose and new discoveries rushed in. But it left behind a lesson. Sometimes the missing ingredient in our picture of the universe is not a new particle or a new kind of force, but an extra direction in which reality can extend. Modern experiments keep pressing on this possibility. At tiny distances, much smaller than the width of a human hair, scientists have tested whether gravity still behaves exactly as Newton and Einstein described. They design instruments to measure faint attractions between carefully arranged objects, searching for any sign that gravity might be fading more quickly than expected over very short ranges. If it did, that would be a hint that some of its pull is spilling into extra dimensions. So far, nature has kept its answer hidden. No clear deviation has appeared. But the tests continue, becoming more delicate and more precise, like someone leaning closer to a locked door. Listening, every new experiment is asking the same quiet question. Is gravity keeping a secret from us on the largest scales? The universe itself joins the conversation. When astronomers look at the way matter is spread across the cosmos, they see patterns that do not quite match what they would expect if space were only three-dimensional. Galaxies spin in a way that suggests there is more gravity than the visible stars and gas can provide. We name the missing mass dark matter and speak of dark energy to describe a mysterious pressure that seems to be pushing the universe to expand faster and faster. Often, these are treated as separate mysteries. Dark matter in one box, dark energy in another, gravity's odd weakness in a third. But some physicists wonder if these are not three different problems at all, but three faces of one underlying truth. If extra dimensions exist, then many of the strange behaviors we see might simply be signs that we are trying to describe a higher dimensional reality with lower dimensional language. You can imagine it like this. Suppose you are trying to understand a solid cube, but you are only ever allowed to see flat slices of it. Each slice makes sense on its own, but when you compare them, contradictions appear. Shapes change from one slice to the next. Edges appear and vanish. The confusion is not because the cube is wrong, but because your viewpoint is limited. In the same way, physics may be telling us that the contradictions we keep bumping into are reminders that our picture is incomplete. The strength of science is that it does not turn away from these mismatches. It does not insist that the simple picture must be right just because it feels comfortable. Instead, it follows the discomfort and traces the edges of the puzzle, allowing the universe to be stranger and richer than we first imagined. Gravity's softness, the mathematical demands of string theory, the early hints from Kaluza and Klein, and the way galaxies and larger structures behave all seem to lean in the same direction. Perhaps the universe carries more layers than we can ever perceive directly. That leads us back to a gentle tension. Do we trust our senses, which offer us a tidy three-dimensional world? Or do we listen to the equations and observations that keep pointing toward hidden directions? That tension, that pull between what we see and what the mathematics suggests, is one of the reasons so many physicists continue to explore the possibility of extra dimensions. The idea may sound modern, like something borrowed from a science fiction story. But it has been present in physics for more than 100 years. At its heart was a very simple question that first drew people toward this path. Could gravity and electromagnetism, the two forces that people understood best at the time, be two sides of the same coin? That quiet question lingered in the air at a very special moment in history. By then, Einstein had already turned the world inside out by showing that gravity was not some invisible tug from far away, but the gentle bending and curving of space and time themselves. A planet did not fall toward the sun because it was being pulled, but because it was following the natural slope in the fabric of the universe. Before that, James Clerk Maxwell had woven electricity and magnetism together into a single force, showing that light itself was an electromagnetic wave. Two separate phenomena suddenly revealed as two notes in the same chord. With those successes, the early 20th century felt charged with possibility. If gravity could be reimagined, if electricity and magnetism could be united, maybe everything could fit into one elegant picture. Like constellations joining into a single shape once you learn how to connect the stars. It was into that atmosphere that a quiet, bold idea arrived. In the year 1919, a physicist named Theodore Kaluza tried something that must have sounded almost playful, perhaps even absurd. To his colleagues, he took Einstein's equations of general relativity, which were written for a universe with 3 dimensions of space and 1 of time, and he asked a simple, daring question. What if these equations described a universe with 5 dimensions instead of 4? On paper, it was just an extra direction, another axis added to the mathematics, nothing you could point to in the room. But when Kaluza carried through the calculation, something unexpected slipped out. The 5-dimensional version of Einstein's equations did not only describe gravity, hidden within them, like a second melody inside a piece of music, were the familiar equations that govern electromagnetism. 2 forces that had seemed completely different in everyday experience, one shaping the fall of apples and the paths of planets, the other responsible for lightning and radio waves, were suddenly emerging from the same higher dimensional framework. Kaluza had not added electromagnetism by hand. It came out naturally, as if the universe itself were saying, if you let me have one more direction, I will show you how these 2 forces are related. It did not feel like a coincidence. It felt like physics rewarding a willingness to think a little bigger. But there was an immediate problem, one that any ordinary person could have asked. If there really is a 5th dimension, where is it? Why do we not see this extra direction, the way we see up and down or left and right? Why does the world look so stubbornly 3-dimensional? That is where another physicist, Oskar Klein, stepped in to refine the idea. He suggested that the extra dimension might be real, but hidden in a very particular way. Picture a drinking straw lying on the ground. From far away, it looks like a simple line, a one-dimensional path stretching from one end to the other. But as you bring your eye closer, you notice that the straw is not just long, it is also round. You can walk along its length, but you could also, if you were tiny enough, go around its circular surface. There is a second direction there, wrapped tightly around the first. Klein proposed that space itself might behave like that straw. On large scales, it looks 3-dimensional, but tucked away at each point, curled up too tightly for us to move through. there could be an additional dimension, real, but so small that even our best instruments cannot resolve it. We live on the length of the straw and never feel the roundness. Kaluza and Klein together had built one of the first true attempts to unify forces using higher dimensions from a single 5-dimensional space. Gravity and electromagnetism emerged side by side, like two shadows cast by the same unseen object. It was a striking achievement, almost too beautiful to ignore. And yet, physics did not fully follow that path at the time. The 1920s and 1930s became the golden age of quantum mechanics. The brightest minds turned their attention to atoms, electrons, and the strange, flickering rules that govern the very small. Probability waves, uncertainty, and the discrete steps of energy inside atoms stole the spotlight against that dazzling new world. Kaluza and Klein's higher dimensional idea felt almost like a side story. Their theory did not disappear. It drifted quietly through the background. A little oddity that some people remembered and others did not. But the seed had been planted. The notion that adding dimensions could bring clarity refused to die. Decades later, whenever physicists tried to bring the forces together again or patch up nagging gaps in their theories, they would find, again and again, that the mathematics seemed to favor extra dimensions. It was as if the equations themselves were whispering, "You are missing something. Look again. There is something deeply human in that pattern." Someone notices a curious connection and proposes a bold idea. At first, it does not catch on. The world is busy with other questions. Then, many years later, when new puzzles arise, people realize that the old, half-forgotten idea had been pointing in the right direction all along. Kaluza and Klein were not playing with empty abstractions. They had stumbled onto a clue about how reality might be structured. A clue that would come roaring back in the language of more modern theories. That history matters because it shows that higher dimensions were not invented to sound exotic or mystical. They grew out of serious attempts to explain why the forces of nature look the way they do, why gravity and electromagnetism and the nuclear forces each have their particular character. Once that door was opened, it became difficult to shut, because the more deeply physicists pushed into the mathematics, the more often those hidden dimensions crept back into view, like the outline of a shape behind a curtain. If Kaluza and Klein planted the first seed, then string theory is the forest that grew from that seed. Interestingly, string theory did not begin as an attempt to describe all of reality. In the late 1960s, physicists were trying to understand the strong nuclear force, the powerful interaction that binds protons and neutrons together in the heart of every atom. A physicist named Gabriele Veneziano wrote down a mathematical expression, a scattering amplitude, that turned out to describe how certain particles, called hadrons, behave when they collide. It fit the data with surprising grace. Others, including Yoichiro Nambu and Leonard Susskind, looked at this success and began to wonder what kind of picture of the world could sit behind those equations. They developed what was called the dual resonance model and eventually realized that the mathematics looked very much like the vibrations of tiny, relativistic strings. In this emerging view, the basic building blocks of nature were not point-like dots with no size, but tiny loops or segments of string, so small that they would forever appear as points to our eyes. Each string could vibrate in different ways, and each pattern of vibration would show up to us as a different kind of particle. One mode might appear as an electron, carrying charge and a certain mass. Another as a photon, a particle of light. Another as one of the quarks that make up protons and neutrons. The properties of a particle, its mass, its spin, its charges could be thought of as the signature of a particular musical note played on the same underlying string. In more refined versions of the theory, strings could give rise both to particles that carry forces, called bosons, and to particles that make up matter, called fermions, all within a single framework. It was as if the universe were built from the vibrations of a silent cosmic instrument. For a while, this seemed both strange and deeply elegant. But as physicists pushed further into the equations, the theory began to make demands of its own. When they tried to keep everything confined to the familiar 3 dimensions of space and 1 of time, the mathematics misbehaved. Infinities appeared where there should have been finite answers. Symmetries broke in ways that made no physical sense. The structure shook itself apart. The only way to make the theory consistent, to keep it from collapsing under its own contradictions, was to give those strings more room to move, not just one more dimension, as in the old Kaluza-Klein idea, but several. Different versions of the theory asked for different numbers, but all of them needed more than our everyday experience offers. The earliest form, called bosonic string theory, astonishingly required 26 dimensions in total for the numbers to line up. That sounds almost impossible to picture. Later, when physicists introduced supersymmetry, a delicate balance between bosons and fermions designed to make the theory more realistic and stable, the modern superstring theory settled on 10 dimensions, 9 of space and 1 of time. Then, another step was taken. An even broader framework, known as M theory, emerged, weaving together the different versions of string theory into a larger picture. In that view, reality appears to need 11 dimensions altogether. If you count time as one of them, the universe may not be 4-dimensional in the way we usually say, but 10 or 11-dimensional, a structure far richer and more layered than anything we can sense directly. This was not a matter of taste or fashion. It was not something scientists could simply decide to ignore if they found it uncomfortable. Within string theory, the extra dimensions are not optional decorations. They are part of what allows the whole structure to stand. Take them away and the internal consistency begins to crumble. That is a difficult idea to sit with, because it asks us to accept that the world we move through, with its 3 clear directions and its steady flow of time, could be only the visible slice of something much larger. The extra dimensions would still be there, all around and within us. But hidden, this is where the old idea of compactification returns. The same basic picture that Klein sketched so long ago. In string theory, the extra dimensions are thought to be curled up or folded into shapes so tiny that even the most powerful microscopes and particle colliders cannot see them. They do not announce themselves with extra directions you can point toward. Instead, they show up only as subtle influences on how particles behave and how gravity acts. Crucially, these hidden shapes are not arbitrary. String theory suggests a whole family of possible geometries for the compactified dimensions, known as Calabi-Yau manifolds. You can think of them as intricate, many-dimensional surfaces. knotted and folded in ways that are hard to picture but precisely defined in mathematics. Each Calabi-Yau shape represents one possible way for the extra dimensions to be wrapped up, and the choice of shape is not cosmetic. It changes which vibrational patterns are available to the strings, and therefore which particles and forces can exist in that version of the universe. Different shapes mean different physical laws, different menus of matter and light. That is where the picture starts to feel almost overwhelming, because the number of possible Calabi-Yau shapes is enormous. The strange thing about string theory is that it doesn't hand us a single, lonely universe. Instead, it opens a whole landscape, an enormous field of possible realities, each with its own laws, its own flavors of matter and light, its own unfolding story. Some physicists find that unsettling, like trying to choose a single melody when the air is crowded with countless songs. Others see it as a gentle hint that perhaps our universe is only one glow among many, a small lantern flickering in a much wider multiverse. As this idea evolved, it gave rise to something even more expansive, the notion of brains, short for membranes. In this picture, strings are not the only fundamental objects. There can also be higher dimensional surfaces, great sheets, or bubbles, or volumes that stretch across directions we cannot sense. And our entire universe, with all its galaxies and dust, and people whispering into the night, might be sitting on one of these brains. You can imagine it like a soft, flat sheet drifting in a space that has more directions than we can ever turn toward. Everything, familiar particles, light, the fingerprints of chemistry, the warmth of stars could be bound to that sheet, unable to slide off. Meanwhile, gravity, subtle and diffuse, would be free to reach beyond it, exploring the higher spaces between the brains like a wandering ripple passing through deeper water. If that were true, gravity's weakness would no longer be a mystery. It would not be weak at all. It would simply be spread thin across dimensions we cannot enter. Its strength diluted by reaching far beyond our confined world. The idea is not just a philosophical musing. It carries real consequences. If gravity can drift into higher dimensions, then, in particle colliders, those rings of lightning, where matter is pushed to tremendous energies, we might see tiny hints of that escape. Energy could disappear from an experiment, as if slipping through a crack in space, or miniature black holes might form and vanish almost instantly, leaving behind a faint signature like a footprint in dust. Nothing like that has shown up yet, but the search continues, quietly, insistently. The possibility is too meaningful to let go of, because if even one such hint were found, it would change our understanding of reality forever. What makes string theory so captivating and so endlessly debated is that it is not simply an adjustment to old ideas. It is an entirely new framework. It demands more dimensions. It offers a graceful path toward unifying the forces. It gives physicists a way to speak about gravity and quantum mechanics together, without the two languages breaking into argument. That last part is especially important. For decades, people have tried to weave Einstein's smooth, continuous space-time together with the jittery, probabilistic world of quantum fields. Each attempt frayed somewhere infinities rose up. Contradictions tangled the logic, and the two great pillars of physics seemed determined to repel each other. But string theory suggests that the discord fades when the stage is enlarged. The extra dimensions are not decoration. They are part of the instrument. The extra strings on the cosmic harp, of course. Nothing this bold escapes criticism. Some physicists argue that string theory allows too many universes, too many shapes for the compact dimensions, too many ways things could be. They say it risks explaining everything and therefore explaining nothing. They are not wrong to raise those concerns. Physics must always return to the world it tries to describe. It must make claims that can, at least in principle, be tested. And yet, even its skeptics acknowledge something striking. The mathematics did not gently invite extra dimensions, it insisted on them. No one went searching for 11-dimensional space because it sounded mystical. The equations simply refused to behave unless the unseen directions were included. It was as if the logic of the universe tugged at the sleeve of those who studied it, saying, "I am larger than you think." That stubborn elegance is why the idea has endured through decades of debate. It continues to spark new insights, bridges between gravity and quantum entanglement, fresh ways to describe black holes, even ideas that echo into condensed matter physics. It keeps pointing toward a deeper structure, one that ties together information, geometry, and space-time itself. And string theory is not alone in hinting at these hidden directions. Other approaches, like loop, quantum gravity, or models of warped geometric space, also find themselves circling the same possibility. Whenever modern physics pushes against the edge of its comfort, there they are again, those quiet, extra dimensions, returning like a refrain. Once physicists began taking that possibility seriously, a natural question formed: if extra dimensions exist, how are they shaped? Are they tiny, curled so tightly that nothing could slip inside them? Are they broad and stretched out, but inaccessible for some deeper reason? Do they bend and warp the fabric of space so strongly that their presence is felt only by the faintest echoes, because adding another dimension is not a simple yes or no gesture? It is the opening of a whole design space, each layout leading to a different kind of universe. The most straightforward image is the one we touched earlier: compactified dimensions. This is the spirit of the old Kaluza-Klein idea, carried forward into modern physics. Picture a thin wire stretching across a room. From far away, it seems like a single line, but come close enough, and you see that it has thickness. A tiny creature, far smaller than an atom, could walk around its circumference. That hidden path was always there. It was simply beyond our scale. If the extra dimensions of reality are compactified like this, they might be curled into tiny loops, smaller than anything our microscopes can touch. They would be real, just impossibly small. Their presence could only be detected through subtle hints: a particle behaving differently than expected, gravity bending with the slightest irregularity. Then came a more daring idea. In the late 1990s, 3 physicists, Nima Arkani Hamed, Savas Dimopoulos, and Gia Duvali, suggested something now known as the ADD model. They asked a startling question: what if some of the extra dimensions are not tiny at all? What if they are large, maybe even the width of a human hair? At our scale, that still feels impossibly small. But in particle physics, the width of a hair is enormous. In this picture, the familiar particles and forces cling tightly to a 3-dimensional brain, like insects that can walk across a table but cannot leave its surface. Gravity, however, does not share this confinement. it can drift into the larger dimensions, thinning out as it spreads across them. If that is true, then experiments measuring gravity at extremely short distances should eventually see a deviation from the traditional Newtonian pull. For 20 years, physicists have pushed deeper into these tiny scales, down to about 50 micrometers, always looking for the faintest sign of an unexpected weakening. So far, gravity has kept its secrets, but the listening continues. Another variation approaches extra dimensions from a different angle, the idea of warped geometry. Physicists Lisa Randall and Raman Sundram proposed that the extra dimensions do not need to be flat or uniform. Instead, the fabric of space could be stretched and distorted, like a rubber sheet pulled unevenly. In such a warped landscape, gravity could gather in some regions and fade in others. A hidden dimension could be enormous, yet invisible, concealed not by its size, but by the way space-time bends around it. In their model, we live on a three-dimensional brain within this warped space. Everything we know is tied to it, while the true structure of the cosmos extends far beyond our reach. And still another approach imagines something more democratic, universal, extra dimensions. In these models, not only gravity, but all particles and forces are free to explore the higher space. Every known particle would have heavier companions, echoes of itself, arising from motion in the extra dimensions. These are called Kaluza-Klein excitations, a nod to the old seeds planted a century ago. If such heavy partners exist, they could even serve as candidates for dark matter, the unseen mass that shapes galaxies and binds the cosmic web. Experiments searching for dark matter, in their own quiet way, are also probing whether these universal extra dimensions might be real. Each of these ideas about extra dimensions, whether compactified, large, warped, or universal, is like a different lens held up to the same sky. Each one tries to soften a particular puzzle that has nagged at physicists for years. Some focus on the hierarchy problem, that quiet mystery of why gravity seems so fragile compared to the other forces. Others grow from the old dream of unification, the hope that all the forces of nature might one day sit under a single, graceful roof. Still others tilt toward cosmology, trying to make sense of dark matter, or the way the universe's expansion seems to be speeding up as if pushed by some invisible hand. What ties all these models together is simple and profound. They all depend on dimensions beyond the three we move through. They all suggest that the universe we see might be just one thin slice of a much thicker reality, the visible surface of a structure that extends further than we can imagine. The variety of these models is not a sign of confusion, but of commitment. If extra dimensions were merely a fanciful story, they would appear once or twice and then fade. Instead, you see them return in different frameworks, developed and refined over decades, each one trying to answer a slightly different question. When independent paths keep circling back to the same destination, it is worth asking if that destination might be real. The most striking thing is that these models do not remain floating in abstraction. They reach out toward the world, offering specific ways in which the hidden structure of space might reveal itself. If only we are careful and patient enough in our watching. Some predictions involve the tiniest shifts in how gravity behaves at small distances. Others propose new particles, heavy echoes of the ones we know, that could show up in the sprays of debris inside particle detectors. A few even allow for the possibility that if enough energy is concentrated in a small region, the fabric of space could collapse for a heartbeat into miniature black holes, which would then evaporate almost instantly, leaving behind a characteristic pattern of particles. Any of these outcomes would be like a smoking gun for extra dimensions. A clear sign that the stage we live on is deeper than it looks. We have not seen such signals yet, but the search is still unfolding. Future upgrades to the Large Hadron Collider and new instruments like the Laser Interferometer space antenna for measuring gravitational waves from space promise to carry our reach a little further. Extra dimensions, in this sense, are not a single polished picture that everyone agrees on. They are a family of related ideas, each with its own strengths and frailties, each leaving its own set of fingerprints for experiments to look for. Taken together, they sketch a landscape in which our familiar three-dimensional view of space is more like the opening chapter than the final page. It is one thing to whisper that extra dimensions might exist. It is another to ask the harder question that sits beneath the whisper. How could we ever know? Physics is not content with beautiful thoughts alone. An idea may be elegant. Its equations may flow like poetry. But for it to become part of our understanding of the universe, there must be some way to confront it with reality. There must be a trace, a mark, a pattern in nature that could not be there unless the idea were at least partly true. That is where the story becomes both fascinating and difficult. If extra dimensions are real, they have to be hidden well enough that we do not bump into them in daily life. You can move around your room without ever feeling a fourth spatial direction tug at your sleeve, and yet they cannot be so perfectly concealed that they leave no trace at all, or we would never have a chance of finding them. The most obvious place to look is gravity. Among all the forces, gravity is the most suspicious when it comes to hints of higher dimensions. The electromagnetic force acts on charged particles. The strong nuclear force binds quarks deep inside atomic nuclei. The weak force governs delicate transformations and radioactive decays. They are all very particular in what they touch. Gravity, by contrast, is universal. Anything with mass or energy feels its pull. That universality makes it the most natural candidate to slip into extra dimensions. If gravity can spread into more directions than the ones we see, its behavior should change at small distances. Normally, in a three-dimensional space, the strength of gravity diminishes with the square of the distance, double the separation, and the pull drops to a quarter. That familiar inverse square law is what you get when a field spreads out over a three-dimensional volume. But if there are extra dimensions, and you get close enough that gravity can explore them, the fall-off would become steeper. The field lines would have more room to fan out into, and the pattern of their fading would carry the imprint of those hidden directions. To test this, physicists have built some of the most delicate experiments imaginable. Picture a thin metal plate hanging on a fine wire, shielded from vibrations, wrapped in layers of protection against stray electric and magnetic influences. Nearby, another mass is moved gently closer and farther away. The only significant interaction between them is gravity, the faintest of pulls. By watching how the hanging plate twists, researchers can measure tiny deviations from the expected attraction. This is the kind of sensitivity required to ask whether gravity behaves differently at sub-millimeter distances. Scales far smaller than a grain of sand, instruments such as torsion balances, neutron reflectometry setups, and intricate quantum optomechanical devices have all become part of this quiet effort for decades now. Experiments like these have pushed closer and closer to the point where certain models of extra dimensions would have to reveal themselves if they were real. So far, the results match the predictions of Newton and Einstein. No unexpected weakening has shown up, but that negative result is not empty. With each new measurement, the window narrows. The experiments tell us that if extra dimensions do exist, they must be smaller than the scales already probed, or they must influence gravity in more subtle ways than the simplest models suggested. The next hunting ground lies in high-energy particle collisions. The Large Hadron Collider at CERN, a vast ring buried beneath the border of France and Switzerland, accelerates protons to speeds close to that of light and smashes them together. For an instant, enormous amounts of energy are squeezed into tiny regions of space, recreating some of the conditions that existed just after the Big Bang. If extra dimensions are part of reality, then these collisions might shake them, like knocking on a wall to see if there is a hidden room behind it. One possible sign is missing energy. In each collision, we know how much energy goes in, and we carefully measure the particles that come out. If the accounting does not balance, if some of the energy seems to vanish sideways into nothing, it might be a sign that it has slipped into an extra dimension, carried away by particles we cannot detect because they do not live fully on our brain. Detecting this missing transverse energy is tricky. There are many ordinary ways for energy to appear. Missing particles can escape down the beam pipe, or interact too weakly with the detector, or be mismeasured. But even amid that noise, models with extra dimensions predict particular patterns that researchers know how to look for. There is also the alluring possibility of microscopic black holes. According to certain theories, if gravity truly grows stronger at very small scales because it is fed by extra dimensions, then the energies reached in particle colliders might be enough to briefly pinch space into tiny black holes. These would not be dangerous. They would be vanishingly small and would evaporate almost instantly through a process known as Hawking radiation, shedding their energy in a characteristic spray of particles. Such an event would be unmistakable. A sudden, sharp signature that something profoundly new had occurred. Physicists at the Large Hadron Collider have searched carefully for signs like these. So far, none have appeared. But with every round of data, the constraints grow tighter, and the questions become more focused. On larger scales, cosmology offers its own clues. The cosmic microwave background, the faint afterglow of the Big Bang, is like a baby picture of the universe, taken when it was only a few 100,000 years old. Its subtle ripples hold information about the geometry of space, about how matter and light moved in the early cosmos. If extra dimensions are part of that geometry, they could leave fine imprints in those patterns, slightly altering the way galaxies cluster, or the way huge structures form over billions of years. More recently, instruments such as the Dark Energy Spectroscopic Instrument have begun to measure the expansion history of the universe with increasing precision. There are hints, still tentative, that dark energy, the mysterious cause of cosmic acceleration, may not be a perfectly constant background, but something that evolves over time. Certain dark dimension scenarios inspired by string theory imagine a large extra dimension shaping the behavior of the invisible sectors of the universe, gently diluting their interactions and linking dark matter and dark energy as different shadows cast by higher dimensional geometry. If such patterns are confirmed, they could become one of our first observational windows into dimensions beyond the ones we see. Not by revealing a new direction to step into, but by showing how the universe's large-scale behavior bends in ways that are hard to explain otherwise. Gravitational waves add yet another thread. These are ripples in space-time itself. First, directly detected in the year 2015 by the LIGO observatories. When massive objects like black holes or neutron stars collide, they send out waves that stretch and squeeze space as they pass. If gravity can leak into extra dimensions, then those waves might fade differently than Einstein's equations predict, or their frequencies might shift in patterns that betray an extra route for the energy to escape. Our current detectors LIGO, Virgo, KAGRA are only beginning to map this new sky. Future observatories, both on Earth and in space, will be even more sensitive. They might confirm Einstein's theory to an exquisite degree, or they might find small deviations, little bends in the curve, hinting that gravity has more room to roam than our four-dimensional picture allows. And always, in the background, there is string theory. For many years, it has been the leading candidate for a unified description of all known forces and particles. It is ambitious, intricate, and absolutely depends on extra dimensions as part of its foundation. Yet it has also been criticized, sometimes sharply, for being difficult to test in any straightforward way. There is no single experiment we can perform tomorrow that would settle the question of whether it is correct. That tension makes it controversial. Supporters point out that no other framework has gone as far in bringing gravity and quantum mechanics into the same conversation. Skeptics reply that without concrete predictions we can check, it is risky to place too much trust in any one theory. Both sides care deeply about the same thing, finding a description of nature that is not just beautiful on paper, but anchored in what the universe actually does. In recent years, new lines of thought have tried to bring string theory closer to testability. One such effort, often associated with the physicist Qumran Vafa, is known as the Swampland Program. It aims to separate the mathematical constructions that could truly arise from a consistent quantum theory of gravity from those that cannot. Some of these ideas suggest that evolving dark energy or subtle features of gravitational waves might provide indirect ways to probe the underlying structure of spacetime, including its extra dimensions. None of these searches come with guarantees. Extra dimensions might be hidden at energies far beyond what our machines can reach, or folded in ways that make their influence extraordinarily faint. They might be there and yet remain, for us, almost entirely silent. But the breadth of the effort matters. Laboratory tests of gravity at tiny scales, high-energy collisions at particle accelerators, precise maps of the cosmos, and careful listening for gravitational waves are all, in their own ways, asking the same question. Physicists do not devote so much time, creativity, and resources to pure fantasy. They go where the clues point, and in this case, the clues from the hierarchy of forces, from unification attempts, from string theory, from cosmology, keep nudging in the same direction. The potential reward for following them is immense. If extra dimensions are real, then discovering them would be nothing less than rewriting our understanding of reality. We would not notice extra dimensions by stepping through a glowing doorway into some other world the way stories like to imagine. If they are there, they would show themselves in quieter ways, almost shy, a tiny twist in how gravity behaves at close range, a little missing energy in the debris of a collider event, as if something slipped sideways out of our reach, a small change in how quickly the universe spreads out over billions of years. It is like searching for hidden rooms in a house by listening for hollow echoes behind the walls. You might never see the secret space directly, but its presence would change the acoustics of everything around it. That is what physicists are listening for, the faint echoes of dimensions just beyond our touch. And this is part of why the search feels so alive, because if even one of those faint fingerprints turns out to be real, it would not only tell us that extra dimensions exist, it would gently reveal that our picture of space, time, and the universe has been partial from the very beginning. Like waking up and realizing you have been living in only one wing of a much larger house. It is one thing to treat extra dimensions as a clever mathematical fix or a neat way to tidy equations. It is another to pause and ask, with a bit of softness, what it would mean if they are truly part of the world we live in every day, not just as symbols on a page, but as actual directions woven into the fabric beneath your feet. Start with the simplest implication. Our map of reality would be incomplete. For centuries, we have imagined space as three-dimensional, with time flowing along as a fourth coordinate. This framework has served us well, from predicting falling apples to guiding spacecraft around planets. But if extra dimensions are real, then those four coordinates are like the outline of a story missing whole chapters. We have understood the shadow on the wall, but not the full object casting it. Imagine standing in front of a candle and watching your hand's shadow move across the surface. You can learn a lot from that shadow, its shape, its motion, its edges, but you will never feel the warmth of the flame by studying it. You will never know that your hand has depth just from the flat silhouette. That is what our physics might be like if extra dimensions exist. We have been tracing the shadows, while the true shape of reality has quietly extended beyond the screen. If those hidden dimensions are real, the forces of nature might not be as separate as they appear. Gravity could look weak, not because it is timid, but because it is allowed to spread through extra directions, while the other forces remain glued to the three-dimensional space we know. In that higher dimensional view, unification stops being a distant dream and starts to feel like a natural outcome. The four forces we talk about: gravity, electromagnetism. The strong and weak nuclear forces might be different reflections of the same underlying structure, tied together in the extra folds of space. If that picture holds, then the patchwork of physics, with one set of rules for the very small and another for the very large, could finally become a single woven cloth. The deep equations describing atoms and the deep equations describing galaxies might turn out to be different faces of the same story, written in a language that fully embraces those hidden directions. Now let your mind drift outward to the scale of the cosmos. Extra dimensions could gently reshape how space expands. They could influence the way galaxies gather into clusters, and clusters into filaments. Like frost patterns on a window, they might offer fresh ways to think about dark matter and dark energy, those two great shadows in modern science. Right now, we speak of dark matter as an invisible substance, something that does not shine but tugs on stars and gas with its gravity. Dark energy we describe as a strange pressure, pushing the universe to expand faster and faster. But if higher dimensions are part of the stage, maybe both phenomena are side effects of geometry itself. Gravity might spread differently across cosmic distances when there are extra directions to explore. In that case, some of the invisible matter and mysterious pressure we keep inventing could be signs that we have been looking at the world with a flattened map. The implications run even further. In an ordinary three-dimensional universe, traveling to nearby stars takes a heartbreaking amount of time. Even at extreme speeds, distance is stubborn, like a long road under a hot sun. But in a higher dimensional universe, space might be allowed to bend and connect in unexpected ways. 2 points that seem far apart on our three-dimensional sheet could be close together in a folded, higher dimensional sense. This is where ideas like wormholes step into the picture. A wormhole is essentially a bridge through a higher dimension, a tunnel that joins distant regions of space. It sounds like pure fantasy. And for now, as technology, it is, but in a universe with extra dimensions. Wormholes are not just story devices. They are physical possibilities allowed by the mathematics. Even if stabilizing or building one is far beyond anything we can do, they are like secret doors that we know could exist in principle. Even if we have no tools to carve them yet. Then there is the question of the multiverse. String theory and related frameworks do not only require extra dimensions, they allow those dimensions to curl up and warp into many possible shapes. Each distinct shape changes which particles can exist and how they interact. Like altering the design of an instrument and changing the notes it can play. That means each way the extra dimensions are arranged corresponds to a different possible universe, with its own laws of physics, its own strengths of forces, even its own constants of nature. Our cosmos might be just one bubble in a vast, higher dimensional sea. One configuration among countless others. It is a staggering thought. The universe that feels total to us could be one branch on a much larger tree. If you take that seriously, it does something to the way we think about ourselves. For most of human history, we have assumed that our senses, though limited, show us the basic structure of the world. Eyes give us shape and color. Ears give us sound. Skin gives us warmth and pressure. But if there are dimensions our senses cannot touch, we are like fish in a quiet pond, believing the whole world is water because we have never lifted our heads above the surface. We might be exquisitely tuned to a narrow slice of reality, unaware of the larger structure unfolding just beyond our reach. That realization is not only scientific, it is philosophical. It gently forces us to admit that our intuition about what is real is shaped by biology, not by the full richness of the universe. There is also a faint, distant technological note in all of this. If higher dimensions are real, then far in the future, far beyond our current abilities, there might be ways to interact with them. That sounds wild now. The kind of thing you would hear in a late-night story. But electricity once lived in thunderclouds and static shocks before it became something we could wire into lamps and phones. Nuclear energy was hidden in the hearts of atoms long before anyone imagined using it. If extra dimensions can be accessed or gently influenced, they might open doors to technologies we barely have words for, faster ways to move across vast distances, new methods of storing or transmitting energy, Perhaps even modes of communication that sidestep some of the limits we associate with light and distance. These are speculative, yes, and rest far beyond any current design. But they grow from the same soil as the serious physics that hints at higher dimensions. Perhaps the most intimate consequence, though, is not about travel or technology or even unification. It is about wonder. If extra dimensions are real, they tell us that the universe is more layered, more intricate, and more surprising than we thought. Each major step in physics has carried that same message. We learned that the Earth is not the center of everything, but a small world circling an ordinary star. We learned that time does not tick at the same rate for everyone, and that space can curve and stretch. We learned that matter is not solid all the way down, but mostly emptiness, threaded with quantum uncertainty. Extra dimensions would be another step along that path, a reminder that the world we see is not the whole world, just the part our senses and instruments can currently touch. So what would it mean if they are truly there? It would mean that our universe is larger than our perception, richer than our imagination, more intricate than any diagram we have drawn so far. It would mean that we have been walking across the surface of a deeper structure, one that might help tie together the loose ends of physics and open doors we did not even know existed, and those whisper-soft ideas, wormholes, multiverse, shortcuts through space that we usually keep in the realm of dreams, might not be dreams at all. They might be glimpses of the architecture beneath reality, seen through a glass that is still fogged. Where does all of this leave us? Here and now, we have a century of hints, a whole forest of theories, and a mountain of mathematics that all seem to murmur the same possibility. There may be more than 3 dimensions of space, but science does not move on murmurs. It moves on evidence. That is the hard part. After all this time, we still do not have a direct, undeniable proof that extra dimensions exist. What we do have is a picture that is both frustrating and thrilling. Frustrating, because the clear signatures remain hidden. Thrilling, because we have never been closer to the edge of where those signatures might appear. So for the moment, the status of extra dimensions is something like this. We have not found them, but we have not ruled them out. We have looked for their traces in delicate gravity experiments, in high-energy collisions, in the glow of the early universe, in the ripples of space-time from distant collisions, and the path forward is still open. Every experiment that returns with no sign does not close the book. It sharpens the questions. It tells us where not to look and narrows the places where they might still be hiding. Science is as much about elimination as it is about discovery. The bigger picture is that extra dimensions remain one of the boldest, most far-reaching possibilities in modern physics. They are not a decorative flourish. They are a possible key to some of our deepest mysteries. Why gravity is gentle, how the forces can be unified, why the universe expands the way it does, and whether our cosmos is alone. Right now, we stand at a kind of crossroads. We have theories that reach beyond our intuitions, instruments that keep improving, and the patience to continue listening for faint signals in the noise. The answer could arrive as a tiny deviation in a tabletop experiment, a strange pattern in collider data, or a subtle quirk in ancient light from the early universe. Any one of those could turn the question of extra dimensions from a possibility into a discovery. History has a habit of rewarding careful attention to whispers. The odd orbit of Mercury, the puzzle of ultraviolet light from hot objects, the quiet prediction of antimatter, all of them began as small mismatches, almost easy to ignore. And each one opened a new chapter in our understanding of reality. Extra dimensions may still be waiting in the shadows, but the search for them is one of the most exciting hunts in science today.